To continue the discussion on primary-secondary pumping, there are numerous other applications of single pump usage for primary-secondary usage, many times in industrial plants. This would illustrate, for example, the use of a crossover bridge with a stop-start secondary pump providing heat as for a heat transfer storage unit. When the temperature control tells the pump to start, in order to maintain temperature, the pump simply starts, drives water through the heat transfer in the storage tank, providing the necessary heat. This would be used for water temperatures less than about the order of 225 degrees Fahrenheit. In many cases, primary-secondary pumping has been used for very high temperature systems, at times corresponding to the order of 300 degrees Fahrenheit, or over and above low temperature, low pressure code limitations. But we can use a small secondary pump in an application such as this by simply placing the pump on the return side of the secondary circuit. Because so long as we are providing water in the storage tank at, let us say, a temperature of 140 degrees, the pump will not be subject to the high temperature limitations otherwise imposed on that pump. And we can take a very high temperature drop across the distribution main corresponding to those temperature drops normally associated with water systems operating at 400 degrees Fahrenheit, and compete very, very closely with those types of systems in terms of reduction of flow through the primary distribution main. There are, as stated before, many applications for the usage of single pumps in terms of primary-secondary applications, which simply can't be covered in terms of time. Let's illustrate then some of the further continuation that we had in terms of primary-secondary pumping development. This slide again illustrates a crossover bridge interconnected with the primary distribution main. Now, for this illustration, we will have a secondary circuit, which could be a heating comfort area with terminal units, and or it could again be a storage tank as applied, for example, in an industrial area. And we'll have a secondary pump, which is going to pump a constant flow rate through that secondary zone, and or we could apply, of course, two-way control valves to the terminal units associated with that secondary zone. Now we'll connect that from the secondary circuit to the primary circuit by two bleed lines. In this case, each bleed line being relatively close together so as to not cause any pressure drop in the bleed lines themselves. Now these bleed lines will bleed, in this case this being intended for hot water application, the necessary flow rate into that circuit and out of that circuit to maintain the required temperatures for the secondary system, whether this be for comfort heating and or whether it be for a storage tank application. We can then apply an injection pump into the bleed line. And in each bleed line, we'll place a flow control valve. Now, on a call for heat, in the secondary zone, the pump will actuate and will drive the necessary flow rate from the primary distribution main into the secondary circuit. The manner in which this will work will be that the pump will cycle, and will cycle relatively frequently, depending on the load, of course. We can, of course, provide reset for a comfort heating application by a reset control, indoor-outdoor, applied to the pump. So let's go through this example then and determine as the flow rate need we may have for the injection pump as contrasted with the secondary circuit. Supposing in that secondary circuit we had a water temperature need of, as a mean water temperature of 150 degrees. And we're going to circulate this at a 20-degree temperature drop. This would establish then that we would have 160 degrees as supply water temperature, 140 degrees as return water temperature, and we would establish a flow rate need of 40 GPM based on the load of 400,000 BTU. Now let's contrast that with the flow rate need in the primary distribution circuit. The primary distribution circuit, we're going to provide water at a temperature of 240 degrees Fahrenheit. We have 140 degree water returning from the secondary circuit. And that 140 degree water will proceed through the bleed line when the pump is on, and will establish, if we have the secondary circuit crossover bridge in proper flow balance, that we are returning 140 degree water to the basic distribution system. Now, if we provide 240 degree supply and return at 140 degree return, we have a 100 degree temperature drop across the distribution main. We have a 20 degree temperature drop across the secondary circuit. So we need only provide then 20 divided by 100, or 1/5 the flow rate in the primary distribution main that is going to be used in the secondary circuit, and that must be provided by the injection pump. This would mean that our actual need for flow rate is 8 GPM in the primary distribution main, and our pump need only provide 8 GPM in terms of injection pumping when it starts its flow rate. So the necessary thought provision here then is what will happen to flow in the common piping. In this illustration, we have common piping also in the secondary circuit. In order to understand how flow in the common piping affects mix and operation of a system using primary-secondary pumping, we shall have to establish an ancient law which basically states that flow into a T must equal the flow that leaves the T. In this circumstance, we'll consider the T connecting the bleed line into the secondary circuit. We will have, as you remember, a flow rate of 40 GPM pumping out of that T and into the secondary circuit under the influence of the secondary circuit pump. Now, into the bottom of that T, we will, under the influence of the injection pump, provide 8 GPM flow rate. So we're leaving at 40, injecting 8, which really means that we must now provide a bypass, or this will automatically happen, of 32 GPM. The bypass water flowing into that T must be at the water temperature of 140 degrees. So what we have happening then is that we have 32 gallons per minute of water at 140 degrees, mixing with 8 GPM of flow at 240 degrees, providing a mixed water temperature of 160 degrees at 40 gallon per minute flow rate. This is a very, very simple application of injection pumping that has been widely used and works well because the B&G booster pump can stand continuous cycling in terms of injection without any difficulties at all. The only important point is that we have to adjust the pump so that we get out of the starting winding mode in terms of operation of that pump. Given that circumstance, we have, for example, an injection pump in our schoolhouse used for control of baseboard water temperature and panel heating, which has been in operation for 25 years without ever having a need for service except for an occasional oiling of the pump. We can, because of the quick and instantaneous cycling of the pump, maintain incredibly close control of water temperatures in the secondary circuit, whether this, in this case, be on reset or for a single water temperature. Another application that has been widely used in Washington, D.C., as basically for many years the basic method of providing for domestic water is to utilize an instantaneous heat exchanger with a circulation pump that provides a continuous flow through the exchanger itself. And it can and must be true that water temperature exiting from the instantaneous exchanger cannot exceed the water temperature available in terms of the shell water temperature. We now provide an injection pump controlled to a water temperature of 140 degrees, so that should the water temperature decrease inside the shell of that exchanger due to a domestic water draw, the injection pump will simply inject heat into the constantly circulating loop around that exchanger so that we maintain then very consistently a water temperature leaving the exchanger of 140 degrees. This has been used for a great many years in this area and again was basically established because of problems associated with conventional control in which the water temperature leaving the exchanger was very high, it fluctuated widely, and did indeed cause some troubles with people in showers getting scalded and having problems such as that. This solved the problem, but is indicative of the close control that can be achieved by injection pump operation. Another application that has been widely used, this many times in terms of storage, is to provide a storage tank pump with an injection pump is running from a heat exchanger into the pumped loop for the storage tank. And again, we can establish extremely close and tight control for a system utilized in this manner. Now, another application for the single pump that followed from this initial discussion, this many years ago, was to provide injection pumping as from a boiler for reset and injection pumping as from a chiller for control of chilled water temperature. During the summertime, we operated the chiller and its pump. During the wintertime, the chiller and its pump were shut off. The boiler injection pump then provided the necessary reset temperature for the secondary circuit. Let's continue now, and again, there are many applications for injection pumps that have been used and applied simply based on the very simple conceptual ideas that if in primary secondary pumping we provide the necessary common piping which has a low pressure drop, we can completely disassociate the pumping of a primary loop as from the secondary loops. So let's proceed then into other illustrations of primary secondary pumping using other control methods. Following the initial inception of primary secondary pumping, the introduction of various types of control devices applied around the primary secondary interconnection to the distribution system was introduced. And this was basically established by the control people, who found a great advantage in terms of primary secondary usage because the primary secondary type of system reduced the very large commercial system from a single large pump into basically a number of small pumps, as these would affect the control valve operation on the system. And they had had a great deal of difficulty because of overheaded pumps working on single two-way control valves, as illustrated here. Had a single small pump now, controlled by two-way control valves, and because this single small pump was the only pump affecting operation of the secondary circuit, we had much lower pump heads driven against the control valves so that the systems worked then quite well without the enormous pressure differential rise problems that could otherwise and quite often do occur when a single large pump is driven against the control valve itself. The fact of usage of the smaller secondary pumps eliminated problems. Now, the introduction of control into these systems then led to a series of methods of control for the secondary circuits. And let's investigate these methods as applied. The initial thought was to provide these many years ago, in which energy costs were low. We had then a constant flow through the crossover bridge. The interconnection in terms of common piping was again followed, so that we had basically then a relatively low pressure drop in that common piping for disassociation pumping service. And a two-way valve, three-way control valve rather, was installed, this being a mixing valve, at the inlet side of the secondary circuit. And this was applied for some years until it was discovered and thought of that the pressure drop of the three-way mix valve was relatively high relative to the suction of the secondary pump. We could on occasion run into PSH or cavitational problems because of this. The other statement was this, that many times the secondary circuit pipe size was considerably greater than the pipe size used in the crossover bridge line and for the inlet bleed line into the bottom of that control valve. This made the three-way valve then act rather as a sewer in terms of the flow it was attempting to control, and led then to some difficulties because of the oversizing of that valve relative to the actual distribution system. So let's change that and illustrate the changes that occurred once this was developed. And the simple change was this. We placed the mix valve in the crossover bridge, sizing that mix valve to the size that we had as necessary for the proper flow distribution into the crossover bridge itself. This meant the valve was smaller. Because it's smaller and because it was sized to the flow rate it was actually controlling, which is the flow rate in the bleed line from the crossover bridge and into the secondary circuit. We then had better control at a lower cost. The other potential thing that was done was to provide a diverting valve in the secondary circuit, a diverting three-way valve in the secondary circuit. And that diverting three-way valve eliminated the problem inherent to providing pressure to the pump suction in the secondary circuit. But basically, the true solution was to use the mix valve in the crossover bridge. Because the valve was smaller, it being a mixed valve, it cost less than a diverting valve. We still had the direct injection of pressure from the primary circuit into the secondary pump suction and solved a great many problems. It is necessary, of course, and this should be continuously reemphasized, that we flow balance on any system such as this which has a constant flow rate, because the discussion so far for these systems has been to a constant flow rate in the primary circuit. And what we're doing with this then is to change the flow rate introduction from the primary circuit and into the secondary circuit by operation of the control valve. This has been illustrated for the single pump, for the injection pump, and now for three-way control valves, with the three-way control valves again generally being applied as a mix valve in the crossover bridge itself, and our common piping change is now from the crossover bridge and into the secondary circuit. It will be noted, however, that we still have the disassociation of pumping of the secondary circuit from the primary circuit because of the very low pressure drop in that common piping. Now, a third development that occurred later has to do with a diversified flow in the distribution system and or a variable flow rate through that distribution system. And what we would do in this circumstance then is to change the distribution in such a way that we maintain the common piping in the crossover bridge. but we provide control by means of a two-way control valve in the crossover bridge supply or return. It makes no difference in terms of flow rate as to whether that control valve, this two-way control valve, is applied in the return side of the crossover bridge or the supply side. It only establishes a difference in terms of the static pressure that we will have developed in the secondary circuit. We have the control valve in the return line. The pressure developed by the primary pump and its compression tank will be delivered directly into the secondary circuit, so we'll operate at a fairly high static pressure. Conversely, if that control valve were changed to the supply side, we would back pressure from the compression tank and into the secondary circuit through the return line so that our static pressure in the secondary circuit itself would become much lower. But the conventional arrangement is to apply the two-way valve in the crossover bridge. And this is applied widely in terms of chilled water application as well as heating application, because by operation of that two-way control valve, we can, by return water temperature control, for example, and by use of a bypass around the two-way control, establish for chilled water a constant return water temperature, which will have a great influence in terms of proper control, for example, of variable speed pumping applications. Now, the two-way valve will control this secondary circuit separate from the control of any other secondary circuit, and will establish, because of this, a high degree of diversity, and will establish disassociation of pumping of the secondary circuit, whether this be a building or a small circuit, from the control of any other circuit applied to that system. So we have established then that we can control primary, secondary circuits, whether these be storage tanks, vats, heating, cooling secondary circuits, by means of single pump, by means of injection pumping from the primary circuit and into the secondary, by means of three-way control valves, with the three-way control valves, if you will remember, being installed in the crossover bridge as a mixing valve, and or by use of a two-way control valve installed in either the supply or return leg of the secondary circuit. And this provides us then with a great variety of potential control methods